Welcome to Chem Lectures, lecture number 3 on kinetic particle theory. So before we begin, let's have a let's dissect this few terms here. Kinetic, what does it mean? Basically means moving. Moving, having energy, kinetic energy, it's moving. Particle basically represents small little bits, and it's a theory. So it's basically a theory of small little bits that are moving. So if we understand how they move and how these little bits are actually arranged, we have essentially understood the entire topic of kinetic particle theory. So before we begin to go into KPT, let's first have a quick overview of matter. Why do we need to know what is matter? So long time ago, before science was advanced, everything was matter and was defined as anything that has mass and takes up space. And it sometimes has different states: solid, liquid, gas, depending on the temperature and the different conditions that it experiences. So matter was anything which has a mass and takes up space. And to man then, these three classes of metals were defined very simply based on their properties. So if something has a fixed volume, fixed shape, cannot be compressed, and it does not flow, we call it a solid. If it has a fixed volume and no fixed shape, basically it takes the shape of its container, cannot be compressed, and it flows easily, we call it a liquid. And if something has no fixed shape, no volume, no fixed volume, no fixed shape, easily compressed and flows in all directions, we call this a gas. So over here, these are balloons with air pumped inside. So long time ago, it was defined as solids, liquids, and gases. But then came along this revelation that matter must be made out of something even smaller. And if you were to break this thing up, if you recall, if you break something into the smallest possible bit, which still has the chemical properties of that particular substance, it would be called an atom. So all the atoms will come together, and they will be arranged, and they will be placed in some sort of manner which gives you the properties of all these three types of matter here. So if all these three types of matter are made up of the same element, or same particle, or same atom, let's say water molecule H2O, why is it so that the water molecule can take on the state of a solid, can take on the state of a liquid, and it can take on the state of a gas? What is the difference between these three states? How are the arrangements? How is it moving differently when it takes up these three different states? So that is what the kinetic particle theory aims to describe. So if we were to summarize everything up, that is just the gist. That is the gist of KPT. So KPT defines particles as discrete, too small to be seen. There are spaces. These spaces are very important. Later on you will see why. The space is different between the solids, liquids, and gases, and the particles are in constant random motion, and they move at different speeds as well. So how did we know that these particles actually exist when they are too small to be seen? So imagine when you spray a perfume, or when you open a packet of extremely fragrant biscuits or some food at the front of the room. People in the room or at the back of the room will eventually smell it. So how did the smell from the food get from one end of the room to the other end? There must have been something which carried the smell over. So the things which carried the smell over are the particles. We can't see them, but they still exist. So this movement from the front of the room, where you open your fragrant bowl of noodles, to the back of the room where there's no bowl of noodles, is called diffusion, and it gives us this indirect evidence that particles actually exist. More specifically, diffusion means that the particles move from a region of higher concentration to a region of lower concentration down a diffusion gradient. So eventually, let's say this is a lump of sugar in water. Eventually, the entire water the entire container of water here will have sugar particles evenly distributed throughout. So this is called diffusion. In some sense, it gives us an indirect evidence for the kinetic particle theory. Alright, sometimes you will see questions which try to link gases to KPT. So they will give you a container and they will say inside it is placed some drops of liquid bromine. What happens at the end of the day? Eventually, bromine will evaporate and it will fill up the entire jar. Why? Diffusion. Recall, from a region of higher concentration to a region of lower concentration. So eventually, this high con area, this is the low con area, eventually you all spread throughout until it is even. Right? So let's go through this step by step. Step 1, evaporates, it fills the gas jar. So imagine this part doesn't exist first. So it evaporates and it fills the gas jar. And if I were to place an empty jar above, eventually this region, because it is more concentrated, the particles of bromine will also diffuse outwards and it will fill the whole thing eventually. Okay, so eventually it will become evenly mixed throughout these two gas jars. It's the same if I were to place a crystal of potassium manganate 7 in liquid. So over here there's a crystal of potassium manganate 7. It is deep purple in color. It dissolves and it slowly spreads throughout the entire container of water until eventually the whole thing becomes evenly purple. So now, since KPT states that there are particles that are moving, something will affect how the particles can move. And these two factors are temperature and mass. So imagine if I have a very heavy particle, it will tend to move slower because you need more energy to move it. If the particle was in an environment of a very high temperature, when there's a lot of heat energy or a lot of thermal energy, the particles gain kinetic energy. So if they gain Ke, it means that they have the ability to move faster. So higher temperatures, particles move faster. Heavier the mass, the particles move slower. So it means that at higher temperatures, my rate of diffusion will be faster. When the mass of my particle is heavy, the rate of my diffusion will be slower. Right? So let's go through them in detail. So particles move faster at higher temperatures. Why? Because there's more kinetic energy. So as a result, they spread around more quickly, which means that the rate of diffusion is faster. Okay. So summarize, increased temperature, increased rate of diffusion. The mass, the heavier it is, the more slowly it moves, the slower the rate of diffusion. Okay, this is inversely proportional. Right, so this diagram here actually tries to explain to you, this experiment here tries to explain to you the relationship between mass, molecular mass, and the rate of diffusion. So over here you'll see that there's a plug of cotton wool here with concentrated ammonia, and there's a plug of cotton wool here with concentrated hydrochloric acid, and there's this little white ring over here. This white ring is actually ammonium chloride. So ammonia reacts with HCl to give you ammonium chloride. So you notice that it is slightly nearer towards HCl than towards NH3. And if you were to look at the ruler readings here, 20, 10. So this is assuming this is about 10 cm, this is about 10 cm, this is about 10 cm. This is 1/3, 1/3, and this is 1/3. So this ring is actually about 1/3. Is 1/3 of the distance between the HCl plug and the ammonia plug. So why is that so? So let's think through this step by step. Number 1, my con NH3 and my con HCl will evaporate. So when they evaporate and they react, they form my ammonium chloride. And if I were to calculate the molecular mass, the relative molecular mass, ammonia is 17, HCl is 36.5. So 17 versus 36.5, this is almost a doubling. So HCl is almost twice as heavy compared to ammonia. Each molecule of HCl is twice as heavy compared to each molecule of ammonia, which means that the lighter ammonia particles can diffuse more quickly than the heavier HCl particles. And because it is twice as heavy, because HCl is twice as heavy compared to ammonia, it means that ammonia can travel twice as fast. Inversely proportional is twice as fast. So if this is 3 parts, this is twice as fast. For every 1 unit this travels, the gas travels 2 units. Okay, so ammonia vapor travels twice as fast as HCl vapor because the relative molecular mass of ammonia is half that of hydrogen chloride. So as a result, the white ring forms nearer towards HCl, and it is 1/3 the distance towards HCl. Alright, so let's have a quick go through of checkpoint 1 over here. Based on the knowledge you have just gained, how do you produce the greatest rise in the water level at X? So you want X to go up, which means that this level must go down. What gas should be gas X? Make a guess. So let's explain this question in more detail. In order for this water level here to go down, something from here must push the water downwards. So there must be a gas inside here, and this gas inside here is oxygen. So how do you make the gas inside here push this water level downwards? There must be more gas inside the porous jar. More gas. So how do you get more gas in the porous jar? My gas X must diffuse in faster than the oxygen gas inside diffuses out. Because if you observe this question here, diffusion means higher concentration to lower concentration, higher to lower. So outside gas X is higher, inside O2 is higher. It means that there's a tendency for O2 to diffuse out, and there's a tendency for X to diffuse in. So X must go in faster than O2 goes out. So for X to diffuse faster, it means that X must have a lower relative molecular mass compared to O2. So if I were to count the relative molecular masses of all these 4 different gases over here, I will come to the conclusion that methane is the lightest gas, which means it will diffuse faster than oxygen, which means that it will enter the porous jar faster than oxygen goes out. So as a result, the pressure inside is increased and it pushes the water level down. Okay, which means X here will rise up. But eventually, at the end of the day, when the concentration of the gases are the same throughout, it will mean that there's no longer any pressure difference. My water level here will fall back to the original level. Alright, so this is the explanation. Methane is the lightest gas, it will diffuse fastest, so it will result in the rise of water level at Y. Okay, over here you see 3 different representations of the states of matter based on KPT. You will need to know how to describe all these 3 different representations. Solids, notice from the diagram, they are all packed very closely together and they are very orderly. Versus liquids, it is still close, but you notice that there's some slight disorder, so it is not orderly. Gases, totally far apart and totally random as well. And because of this close packing in solids, there's very little empty space, which means that it cannot be compressed. Similarly for liquids, because of this very close packing, there's also very little empty space, which means that it also cannot be compressed. For gases, you notice that the large spaces between them means that if I exert a force, I can push the particles closer together. So it allows the gas to be compressed. And for the movement wise, they can't move anywhere, but they will still vibrate about their fixed positions. For liquids, they can move about. They can move freely throughout the liquid. If you pour a liquid, it comes out of the cup. Correct. So why can it flow out of the cup? Because the particles can move freely, and they still vibrate. So long as they have heat energy. So long as it is above absolute zero, all particles will vibrate. For gases wise, again it will vibrate, but this time around it is free to move throughout the container, throughout all the space it is contained within. So if I spray a perfume in the front of the room, at the back of the room you can smell the perfume because the particles can move throughout the room. Okay, so let's try checkpoint number 2. Sketch the different diagrams. Take about 1 minute for this. Alright, so question says that you have a block of ice heated until it forms a vapor. So basically a block of ice is solid state, vapor is gaseous state. So to represent the diagrams, it is simply particles clustered close together in solid state. Make sure you draw all the circles together, and they must be orderly arranged. A vapor is simply particles placed far apart. And to use the diagram, explain why ice cannot be compressed. Why? Because there's very little empty space between the particles versus a vapor. Large spaces between particles which allows it to be compressed. Why does ice have a density of 0.92 versus 0.75 milligrams for water vapor? If you recall, density is mass over volume. In this particular volume, for ice, I have a lot more mass. In this particular volume, let's say I have this square here. If this was a block of ice, I would have a lot more mass compared to a block of water vapor. If this is the block, this is the space which water vapor occupies, probably let's say I have 3 particles of water vapor only, the mass will be extremely low. So it means that the density will be very low as well. Right? Closely packed, very little space, so cannot be compressed. Density wise, same mass over a much larger volume, so as a result, water vapor is less dense than ice. This is something extra. It's about macroscopic properties and microscopic properties based on KPT. Matter may be colored. Particles are not colored. So KPT describes the movement and the positions of the particles which make up matter, but it does not describe the properties, the chemical properties of that state of matter. So for example, gold particles are not gold in color. Okay, the color of gold comes together because of the collective of all the particles interacting together. So it's a bit different. So do not confuse them. Matter can be colored. Particles are not colored. Color is not a property of the particle. It's not a property of matter, but it's a property of the particle itself interacting with other things together. Matter can be hot or cold. Hot or cold basically means when it's hot, it means that the matter has a lot of energy. The particles are vibrating very quickly. Notice I use the term particles are vibrating very quickly. So this vibration comes about because it has more Ke. More Ke results in a higher temperature. The particle itself does not become hot or cold. Okay, it does not become hot or cold. It is the vibration of the particle, the energy possessed by the particle, which gives rise to the property of temperature. And matter can expand, the particle does not expand. Okay, so if this is a solid, the solid expands, the particles move further apart. Particles are still the same. Okay, they're still the same size. They do not expand. Okay, so now let's move on to the next crucial part of this topic, which is a change in state. You will need to know how to describe these changes based on KPT. Solid, notice, closely packed, orderly. Liquid, closely packed, disorderly. Gases, very far apart. So how do we describe the changes between all these 3 different states here? It's quite simple. This is the general way to answer. So let's go from left to right first. So in order for the particles to move away from each other, they must have enough energy. So why are they together in the first place? It's because there's a force which holds them together. So in order for them to move apart, they must overcome the force. So how do they overcome the force? They must gain more energy. So what happens when particles gain more energy? They move faster. So simply, particles gain energy, they vibrate faster, and they can overcome the forces of attraction between them, which allows them to move about more freely. So this is more freely, this is even more freely. So this general explanation applies from left to right. So let's try melting first. So this is a melting curve of a substance. It melts at 69 degrees Celsius. So when it melts, this would be the solid, this would be the liquid section. And over here, this is the melting phase. So before this 69 degrees Celsius, it is solid state. As I give it energy, as I give it more heat energy, the particles absorb energy. They vibrate faster, and they can overcome the forces of attraction between them. So eventually, when the particles overcome all the forces of attraction between them, to a certain extent, it becomes a liquid. So the solid changes into a liquid. Okay, so let's describe each segment in detail. So segment AB, I heat it until it reaches 69 degrees Celsius and it begins to melt. At BC, what happens? The heat energy which is applied to the substance is used to overcome the forces of attraction. So you notice the temperature stays constant. Energy given to it used to overcome the attractive forces, which means that temperature does not rise and it remains constant because all this energy is used to break the forces of attraction between the particles. So after some time, all the solid will melt and I will get the liquid, which is segment CD. Everything has melted, so this is the liquid state. Temperature increases as I heat it until it reaches the next stage, which is the boiling point. So freezing is basically the opposite. Earlier we mentioned, earlier was melting. Freezing is the opposite of melting. So we change the liquid back into the solid. So the explanation is basically the opposite way. Earlier was to gain energy, now is to lose energy. Earlier was to vibrate faster, now is to move slower. Earlier was to overcome, now it is overcome. Earlier was to move more freely, now is to move less freely. So similar graph, but it is basically flipped around. So let's go through each segment again. Temperature drops until it reaches its freezing point, which is actually the same as the melting point. So as it freezes, the particles they move more slowly and they take up fixed positions. Solid particles are closely arranged, orderly, and in fixed positions. So they slow down and they take up fixed positions until eventually the solid state here forms under segment YZ. Temperature also remains constant during freezing. Okay, so eventually all the liquid has changed into a solid. Now boiling is the change in state from liquid to gas. It's the same again, absorbs energy, vibrates faster, overcomes the forces of attraction, and it moves about freely and much further apart. So let's boil off something. Let's boil off this liquid over here. As I heat it, temperature rises until it hits its boiling point. So at its boiling point, it starts to boil. What happens? It absorbs energy, overcomes the forces of attraction holding the particles together, and the particles move far apart and it forms a gas where the particles can move about freely. Condensation is the opposite. Liquid, gas to liquid. So explanation wise, it's exactly the same, but it is in the opposite way. Right? The temperature is the same as the boiling point. Evaporation is a bit different. It is also a change in state from liquid to gas, but it doesn't boil now. It is important to note that evaporation occurs below the boiling point. Anything at the boiling point or above the boiling point, we call it boiling. Anything below the boiling point, we call evaporation. So what does evaporate? Because the particles on the surface have enough energy to escape. So for example, this is a container with, let's say these are the particles of water. So this is room temperature. But I can still get water evaporating off. Why? Because you notice that particles, remember particles are always moving about. So let's say this particle moves and it strikes this particle on the surface. So this particle on the surface gains energy. And say another particle moves and it strikes this particle again, it gains more energy. So eventually, right, this particle will gain enough energy to overcome the forces of attraction between itself and the other particles, and it will escape into the air, into the atmosphere. So this is the process of evaporation. So a key thing to note is that evaporation only occurs on the surface of a liquid. The particles at the bottom of the liquid cannot evaporate off because there's no way it can escape. Okay, particles on the surface, when they are collided upon by other particles, they gain more energy. Eventually, they have enough energy to overcome the attractive forces between other particles and itself, and it breaks away and it forms a gas. Sublimation is a change directly from solid to gas without melting. For example, iodine, you heat iodine, it changes straight from the solid into a vapor. It doesn't melt into a liquid. And that's all for this topic on KBT. So essentially we have covered how the arrangement of the particles can be used to describe its properties. Some of its properties, at least the physical properties. And we have also described the different changes in state based on kinetic particle theory. So see you in the next chem lecture series, and have a good day ahead.